Hi guys, my name's Ali. I'm a PhD student here at Cardiff University, and I'm here today just to give you a quick tour of the gravitational waves lab that we have set up in the basement of the Queen's North building. So let's go in this door here. So this room is the first of our clean rooms. This is actually the electronics room. You can see we've got a lot of instruments that we use to carry out this work. We have a signal analyzer, voltage amplifiers, DC supplies, oscilloscopes, soldering irons, lots of things that you'll probably encounter at some point if you come to do your undergraduate studies here at Cardiff. This is one of the first experiments that I'm working on as part of the PhD. These electronics are actually used in the LIGO experiment, which is a gravitational wave detector out in America. That uses 4-kilometer long interferometer arms. So an interferometer is a device that you make using lasers. And these electronics convert the signal that is sent to a photodiode, so you get a photocurrent signal that then needs to be turned into a voltage that you can use to detect any of these mergers between black holes and neutron stars and things like that. So these electronics should hopefully be added to the LIGO experiment within this year, and they can start being used to make these successful detections, fingers crossed. The next project that I'll show you are these electronics here, which are actually used in a different experiment. These ones are used in an experiment to try and detect a dark matter candidate particle called axions. And so this experiment also uses lasers, and it tries to, if you can pass laser light through a wall, then it proves the existence of these elusive axion particles. And these electronics are actually used to steer the mirrors that are used to align the lasers. So you need really precise alignment in the experiment in order to get a successful detection. And they should be installed out in Hamburg, where the experiment's being built, sometime within this year. And hopefully, again, fingers crossed, we'll get a successful detection from that. Other things we have going on in this room, lots of computers dotted all over the floor. These are all going to be used to control the main experiment we have in the next room, which is a mini interferometer that I'll show you in just a second. And then we have a prototype for a suspended seismic detector, which is still being developed right now. And then lots of other fancy equipment dotted around the walls here. Then coming through this door, we have the cleaner of the two clean rooms. This is our optics room. So, first of all, the optical bench is this big U-shaped bench here. This isolates all of our optics from any vibrations you have traveling through the ground. This experiment will actually be so sensitive that even things like cars driving on the road next to the university can create vibrations which will travel through and enter our experiment through seismic coupling. So we need to isolate our experiment from all of those vibrations, and that's what these benches achieve. The experiment itself is trying to detect something called quantized space-time. So the idea is that we obviously, as we go through our lives, experience space and time as being quite a continuous thing. It's quite a flat thing. But if you zoomed in close enough on a particular piece of space, or if you had a fine enough ruler, the idea is that you might be able to see space taking these discrete steps rather than being a continuous medium that we travel through. And you build something called an interferometer as your ruler that you try and detect these discrete steps with. And so the way it works is we have a really powerful laser here, this coherent laser. I'm going to basically ignore all of these optical components, which is going to really annoy people in my group. So the laser passes straight through all of them, doesn't do anything, comes all the way down the bench, down to this end mirror here. That bounces the laser to this component, which is called a 50-50 beam splitter. It sends half the laser power off to the end mirror down at the far end of the bench there, and half the laser power gets bounced to this mirror here. And then the lasers get recombined back on the beam splitter, so they travel all the way down, travel back, and then via destructive interference, they actually cancel out of this part of the beam splitter here. So this is called the dark port. So assuming that the arms don't change size at all, we get perfect destructive interference and zero light power leaking out of the dark port. But as soon as the laser arms change size slightly, whether it's due to a gravitational wave passing through our experiment and changing the distance between the arms, or if it's due to some additional noise, such as the quantized space-time that we're trying to detect here, you then get a little piece of light leaking out of your dark port, which you send onto a camera, a photodetector. That goes through all these electronics here, and it gives us some detectable signal. So this is actually a really early prototype for the experiment. We've only just achieved our first milestone of successfully locking onto the dark fringe. The final version of the experiment, we're actually going to be building 2 interferometers, so they'll be side by side on this optical bench, and it's all going to be within vacuum as well. So instead of having the laser passing through the components in air, which we have right now, which is not an ideal setup because you get things like scattering occurring as the laser hits dust particles, everything will be housed within a vacuum chamber, which makes it a lot more sensitive to any of these fluctuations that we've been talking about. And hopefully that will be set up sometime within the next 3 years or so. So stay tuned. Hopefully we'll have some successful detection later on in the next couple of years. And yeah, that's about all I've got time for. So I hope you enjoyed seeing what we're doing down here in the Gravitational Wave Lab. And fingers crossed, I see you in Cardiff at some point in the future. All right, thank you.